Hi everybody, in this video we'll talk about quadratic sequences. The first thing we'll do is talk about how we know when a sequence is quadratic. Once we can tell that it's quadratic, we'll talk about steps for finding a formula for the sequence, and then we'll work through a couple of examples. We're going to start with this sequence 8, 17, 34, 59, 92. And probably what you usually would do is look for the difference between the terms. So 8 to 17 has a difference of 9, then 17 to 34 is 17, 34 to 59 has a difference of 25, and then 59 to 92 has a difference of 33. And what we see here is that we don't have a constant difference between terms, so I know I don't have an arithmetic sequence. But something interesting is happening with these differences. So let's take a look at these values. The difference between 9 and 17 is 8. The difference between 17 and 25 is also 8, which we see one more time when we go from 25 to 33. So what we found is the second set of differences are constant, and this is how we spot a quadratic sequence. A quadratic sequence is a sequence whose second differences are constant and non-zero. Its general term is going to have the form t sub n is equal to a n squared plus bn plus c. What this tells us is that linear sequences have constant first differences, but quadratic sequences require us to go one level deeper. So we need to talk about steps to find the values of a, b, and c. So let's assume we're dealing with a generic sequence that's quadratic. Its terms are going to have the form t sub n is equal to a n squared plus bn plus c. Let's find a few terms for our sequence. We'll substitute n equals 1, 2, 3, and 4 to come up with the first four terms. T1 will be a times 1 squared plus b times 1 plus c, which simplifies nicely to a plus b plus c. T2 is going to be a times 2 squared plus b times 2 plus c, which we can write as 4a plus 2b plus c. T sub 3 is a times 3 squared plus b times 3 plus c, which is 9a plus 3b plus c. Then T sub 4 is a times 4 squared plus b times 4 plus c, which is 16a plus 4b plus c. Now that we have the terms, let's find the first differences. We'll start with T2 minus T1, which is 4a plus 2b plus c minus a plus b plus c. This reduces to 3a plus b. Then T3 minus T2 is 9a plus 3b plus c minus 4a plus 2b plus c. That reduces to 5a plus b. Then our last one is T4 minus T3, which is 16a plus 4b plus c minus 9a plus 3b plus c, which becomes 7a plus b. Notice that in all our differences, the c cancels out and we just had to gather like terms. Because this is a quadratic sequence, we don't want to stop with our first differences. We want to move on to the second differences because we know that will give us a constant term. So we'll start by taking our first set of differences. We have 5a plus b minus 3a plus b, which turns out to be 2a. Then our second set of differences was 7a plus b minus 5a plus b, which is again 2a. The fact that we got the same value isn't too surprising because we said quadratics have constant second differences. But let's look at how this helps us. The constant second difference is equal to 2a. So when I'm looking at Tn equals an squared plus bn plus c, a is going to be the constant difference divided by 2. So now we have a quick way to find the value of a. So let's go back to our differences to figure out how we're going to find the values of b and c. We're going to grab the first equation from our first difference, and we're going to grab the first equation from our second differences. What this tells us is that T1 is going to be equal to a plus b plus c, and then our first difference for T2 minus T1 will be 3a plus b. This is going to be the strategy to find the three missing values. We'll start by finding the second difference, dividing it by 2 to get the value of a. Then we'll solve for b by solving T2 minus T1 is equal to 3a plus b. Then we'll find c by solving t1 equals a plus b plus c. Let me show you what that means by going back to our original example. In our original example, we found out that our second difference was equal to 8. That means we can set up 2a is equal to 8, so a is equal to 4. To find the value of b, we're going to use the equation t2 minus t1 equals 3a plus b. We just found the value of a is 4. t2 minus t1 is the first difference of 9 between our first two terms. This gives us 9 equals 3 times 4 plus b. We know 3 times 4 is 12, so we'll just move the 12 over to the left. 9 minus 12 gives us negative 3 as the value of b. Now we just need to find our last value of c. We're going to use the equation t1 equals a plus b plus c. We know a is 4, b is negative 3, and t1 is the first value in our sequence, which is a positive 8. Now we have 8 is 4 minus 3 plus c. 4 minus 3 is 1, which means if 8 equals 1 plus c, c has to be equal to 7. Now that we have values for a, b, and c, we can write a closed form or explicit form of our sequence. We'll say t sub n is equal to 4 times n squared minus 3n plus 7. Let's check our work by calculating t sub 5. This means we should have 4 times 5 squared minus 3 times 5 plus 7. 5 squared is 25, and 3 times 5 is 15. So now we have 4 times 25 minus 15 plus 7, which is 100 minus 15 plus 7. That simplifies to 92, which matches the fifth term in our original sequence. Let's do a second example with the sequence 5, 12, 23, 38, and 57. My first step is to find my first set of differences. I'm going to write that as delta 1. Delta is just a short notation for difference. The difference between 12 and 5 is 7. The difference between 23 and 12 is 11. The difference from 38 to 23 is 15. And then the difference from 57 to 38 is 19. Now we'll do our second differences, which we'll call delta 2. This is where we expect to get a constant difference. We see that 11 minus 7 is 4, just like 15 minus 11 is 4, and 19 minus 15 is 4. Now we can use our formula. We know that 2a will be equal to the constant difference, which in this case is 4. So 2a equals 4, which means a is equal to 2. Then to find b, we use that 3a plus b is the difference between the first two terms, which in this case is 7. We can substitute in our value of 2. So we have 3 times 2 plus b is 7. 3 times 2 is 6. When I subtract 6 from 7, I find out that b is equal to 1. To find the value of c, we're going to use the equation a plus b plus c is equal to our first term, which in this sequence is equal to 5. We'll put in the values of 2 and 1 for a and b to get the equation 2 plus 1 plus c is 5. That tells us that c is equal to 2. Now we can form our quadratic. T sub n is 2n squared plus n plus 2. Now that we have a closed or explicit form for our sequence, we can find any value in the sequence. Let's try finding t sub 15. That means we just plug in 15 wherever we see n. That's 2 times 15 squared, or 225, plus 15 plus 2, which is a total of 467. Let's recap what we just learned. A sequence is quadratic when its second differences are constant and not 0. Every quadratic sequence has a closed form, t sub n equals an squared plus bn plus c. We'll be able to find the values of a, b, and c by using these shortcut equations. 2a is equal to the constant difference, 3a plus b is equal to the difference of the first two terms, and a plus b plus c is equal to the first term. It's important to confirm your work by substituting a known index back into t sub n to make sure you get the same value. Once a, b, and c are known, any term is direct. You just substitute the value of n into the formula, no recursion needed.